Welcome back, I'm that chemist, and today we have another tier list video, and we have some extra special chemicals that we're going to be ranking this time. We're going to be ranking the reducing agents today, which are also known as antioxidants. So the rules for today's tier list is that they must be relatively common chemicals. Additionally, we're going to be considering their utility as reductants, broadly speaking. So without further ado, let's get started. There's many different reducing agents in organic chemistry, but there's a couple that we think of more often than not. And so we'll start with the really common ones like sodium borohydride. Sodium borohydride is nice because typically it will only reduce aldehydes and ketones. It can also do reductive aminations if you have an imine or an aminium. But, it's pretty low in cost, so it's a pretty decent one. There's a borohydride, starts with a B. It's pretty decent. I don't think people hate borohydride too much. Now, the one disadvantage of the boron-containing compounds is that they sometimes form complexes with your product, so they're not super easy to remove and clean up. And so sometimes you'll think you got rid of everything in a quench, but in your workup, when you're concentrating everything down, you'll start getting white precipitate, and that's because you can form borane or boric acid type complexes. Now, fun fact, if you're ever trying to get rid of the last little bit of borane from your reaction mixture, you can actually add in methanol, and that'll form trimethyl borate, and if you just concentrate that away, it'll just pump off on the rotavap. So sodium borohydride's okay, but it's a little bit annoying. Now, another really common reducing agent is lithium aluminum hydride. Lithium aluminum hydride is like sodium borohydride's older brother. It's a little bit more of a sledgehammer. It's able to reduce way more functional groups such as epoxides, esters, carboxylic acids, and so on. So LAH it's a lot stronger. Now the one disadvantage of LAH is if you have it in its neat form, in a powder form, it will slowly disproportionate to other aluminum compounds. And so if you try and dissolve LAH in its powder form, it oftentimes won't dissolve. Now you can get commercial solutions which are a little bit more stable. It's more stable in like THF for instance. And that can be preferable to work with because then you're not dealing with a big clumpy mess. Now, a lot of the time, these reductions will work regardless of if LAH is the active reducing agent, just because there's other possible reducing species. But it's a little bit more annoying for practical purposes to deal with like a big chunky mess. So LAH is pretty good. Um, I'm going to put it in B tier. Now, there's some other ones. So while you might be familiar with LAH, you might not have heard of red Al before, or red aluminum, or this is also known as vitride, as well as some other names. And so this is more of a popular one in industry or in medchem. And this is a little bit more stable than LAH. It's not pyrophoric, but it can still react exothermically with water. Now, the advantage to this is that it can do most of the same transformations. It's a very potent reducing agent. It can still reduce esters, acids, etc. So red aluminum's going to go in A tier. Now, there's other reducing agents which you think of when you're using them, but you don't think of them. If I asked you to come up with a list of reducing agents, you might not think of a lot of these right off the bat. So some of those would include like TDAE. So TDAE, if you're not familiar with it, is an organic reductant. And so these four amino groups are really electron donating. And so this is able to go to a monocation, monoradical species, but it prefers to be in a dication species. So this could be a 2-electron reductant. This is about similar in strength to zinc metal, but the advantage is this is an organic compound. And so this has seen a decent amount of use in organic synthesis, and so it's pretty cool. Now I'm going to put it in A tier as well. Now, if there's any reducing agents that you think I neglected to mention, I'd be happy to hear them in the comment section, as this isn't quite a comprehensive list, but it is fairly extensive. Now, similar to like LAH or red aluminum, you can use alane. And so there's a couple different ways to make alane. One way is to take aluminum trichloride and lithium aluminum hydride and mix them together, and this will form alane. Additionally, you can make alane by treating lithium aluminum hydride with sulfuric acid, and that will just protonate away one of the hydrides. You have to remember that alane itself is a Lewis acid, so it isn't going to react with normal Bronsted acids as easily as LAH would, and so you can produce alane just with sulfuric acid. Kind of counterintuitive. So alane is more potent and more reactive than LAH. It's a little bit scary because explosions can happen sometimes with these. Someone in the Discord had posted a link to this case where a trifluoromethylated pyrazole or pyrrole was undergoing a reduction, and it ended up being an explosive catastrophe. So alane, it's pretty powerful, but it's a little bit dangerous to make and deal with, but it's worth mentioning because most organic chemists won't be familiar with it. So I'm going to put that in C tier. Now, another similar one is lithium triterbutoxy aluminum hydride. And so the advantage of this one is it's kind of like sodium borohydride, but it's also kind of like LAH, but it won't usually reduce esters. So there's a little bit of added selectivity. Now the disadvantage is there's all these big bulky terbutoxy groups, but it's a reagent that's common enough that you'll see it from time to time. I'm going to put it in B tier as well. Now let's move away from the aluminum and boron-based ones for a minute, and we'll pick something more obscure, like ascorbic acid, vitamin C. So this is a good reducing agent. It's been occasionally used in organic chemistry, but it should be used more often due to its availability and how mild it is. There's also other diastereomers of this that exist that various organisms produce, but ascorbic acid is quite common in our diet. So it's a cool chemical. It can do some reductions, but it doesn't have as much demonstrated utility in organic methodology. And since it's vitamin C, we'll put it in C tier. Now, activated rainy nickel. This was a controversial one in the Discord when we were discussing this. So rainy nickel itself is a nickel aluminum sponge. When it's treated with hydrogen gas, it forms a nickel hydride type species. Now, you can actually buy activated rainy nickel from vendors. And so this already has the hydrogen in it. And if you're doing this, or if you're using this in a rainy nickel reduction of a dithiane, which is called a Mazingo reduction, it's actually used stoichiometrically, not as a catalyst, but rather as a stoichiometric reductant, as this forms nickel sulfides. So I quite like rainy nickel, especially in its activated form. And since activated starts with an A, we'll put it in A tier. Really good reductant. It's just a little bit not as great in terms of being wasteful. The other disadvantage is it's a little bit pyrophoric, so if we're running out of space in A tier, I might move this to B tier later on. Now, electricity. You might not think of electricity as a reductant, but you can use electrochemical reactions to oxidize or reduce stuff, depending on what your electrodes are, your cathode and anode, as well as what compounds you have in your solution. So you can do electrochemical reductions. These are less commonly done in a research setting. However, certain labs, such as Phil Barron's lab, extensively do electrochemistry. Electrochemistry is pretty cool, but it hasn't seen as much utility in terms of like broad, wide-scale acceptance in organic chemistry. However, it is pretty convenient. We all have electricity. Now, the disadvantage is reproducibility, which the ElectroSyn hopefully will address. However, people in the Discord have challenged that as well. So because electrical setups have current, we'll put it in C tier. Now we have some other reductants like formic acid. You might not be familiar with formic acid. You might have recalled that I mentioned this in the acid video because formic acid comes from ants, or it can come from ants. But it's actually the equivalent of hydrogen in many reductions. And so this is like CO2 with hydrogen added across it. So formic acid can be a good reductant. It's available. It's usually safe if you're being careful with it. And so I'm going to put it in S tier. I think formic acid is a great reductant. Same with hydrogen. Hydrogen's another really great reductant. If I didn't put hydrogen in S tier, I'm sure a lot of you would give me trouble. It's just like the smallest reducing agent possible, amazing atom economy. You can easily make hydrogen any number of ways, such as the treatment of aluminum with acid or base. Very easy to produce hydrogen, S tier. Mercaptoethanol. So the biologists among us here will definitely be familiar with mercaptoethanol as a reductant for disulfides in peptides. So if they're following some protocol to try and isolate proteins or do whatever it is biologists do, occasionally they'll call for mercaptoethanol. Now, it's also notorious that mercaptoethanol stinks. It is a thiol, and thiols have a bad reputation, and they deserve it. So mercaptoethanol can go right into F tier because it stinks. Okay. Let's pick another one that's kind of fun, like hydrogen iodide. So hydrogen iodide is a good reducing agent for alkyl iodides. However, the formation of I2 can suppress the reduction, and so typically another reductant is required to get HI reductions to go to completion. Now, if you have HI for any reason, people are going to assume you're making drugs with it, and so we're going to put it in D for drugs, drug tier. Similarly, if you use aluminum on mercury, an aluminum amalgam is commonly used for clandestine reductions, as mentioned in Breaking Bad. As this is used for clandestine purposes, this can go into D tier as well for drugs. Now this one here, samarium iodide. I did not come across samarium iodide until I was a grad student, but it's a very useful single electron reductant for several purposes in organic chemistry. Now, the one disadvantage is you have to make sure that your samarium iodide hasn't oxidized. But when you do have good, clean, pure samarium iodide and you carefully handle it, it can be a really useful reductant. I'm going to put it in S tier. If you haven't looked at samarium iodide reduction chemistry before, you should definitely look into it. It's a really useful chemical. Okay, tin 2 chloride. Tin 2 chloride can be used for a few different reductions in organic chemistry. Sometimes you'll see the reduction of nitro compounds. You can usually get selective reduction of nitro compounds, but as I've mentioned in some of my other videos before, nitro groups and the reduction of nitro groups tends to be very case specific to each substrate. So tin 2 chloride, it's pretty cool. It's pretty mild. I'm going to put it in S tier. Good reducing agent. Now we'll give Dibol a shot. So Dibol is a little bit like lithium aluminum hydride in the sense that it can reduce aldehydes and ketones, but most of the time it doesn't do that. Most of the time it's fairly well behaved, and if you have an ester, you can usually reduce an ester just to the aldehyde and it will stop. So Dibol can be used to selectively reduce esters if you're being careful and you don't have too much excess and the workup is done correctly. Now it's fairly finicky, but it does have a place in everyone's heart because you can convert a two-step process, which would be the complete reduction of an ester all the way to the alcohol, into a single-step process where you can just reduce it just to the aldehyde. Now I say a two-step process because normally what you'd do is you'd over-reduce to the alcohol and then oxidize back with something like DMP or swern to get yourself the aldehyde. So Dibol is a little bit finicky. I'm going to put it in B tier. If you disagree with that, make sure you let me know down below. So let's look at carrots. So if you haven't seen the reduction using carrots video, I'll put a link to that here. Now, it turns out that carrots have some sort of keto reductase. And so the keto reductase is able to do an enantioselective reduction of ketones. If the product that's formed is a chiral substrate, you can get decent enantioselectivity. And we didn't really think that this would work, but a couple people in the Discord tested it out. And I'd really encourage you to go check out that video if you haven't seen it yet. So the genus for carrots starts with a D, so I'm going to put it in D tier. Actually, no, we're doing D for drugs, so we'll put it in C tier, C for carrots. Okay, so diimide. Diimide is an old school reductant that is still easily accessible but a little bit dangerous to make. The disadvantage of diimide is it's not that stable, but the advantage of diimide is when you do a reduction with diimide of certain alkenes, you can get a really clean conversion to the corresponding alkane, and then your only other byproduct is nitrogen gas. So diimide is really cool. You used to see it more in total synthesis historically, but I don't think I've even seen it used in the last decade. So diimide's really cool. It's a little bit of a hazard, so I'll put it in E tier. Similar is hydrazine. So you can do a Wolff-Kishner reduction with hydrazine. You can use it as a reducing agent for other purposes, but the disadvantage is it's highly toxic, and when you're working with hydrazine, especially in its free base form, it's pretty terrifying. So I'm going to also put hydrazine in E tier. Now we have the alkali metals, which we haven't touched yet. I decided to exclude cesium, but you can assume that cesium's probably going to go somewhere similar to where these go, except maybe it's a little bit more dangerous, so it's going to go in a lower tier. I personally really like sodium. I think sodium is a great metal. Even when it's in its ionic form, it's still a good metal. You can do some cool chemistry with sodium metal, like you can do dissolving metal reductions. Usually those go through solvated electrons, but not necessarily. And you can reduce disulfides. You can do a lot of different things with sodium. Now, the one disadvantage is sodium can sometimes explode, but the explosions that sodium does are fairly chill. So I'm going to put sodium in S tier, even though it's a little bit dangerous. Now, lithium, on the other hand, is less practical as a reductant. And you might not be aware of this, but lithium metal actually reacts with nitrogen gas. So if you ever want to work with pure elemental lithium, you need to work with it under argon, because it will form lithium nitride in the presence of air. Normally, our main concern is that these metals will react with oxygen, but it turns out that lithium also reacts with nitrogen. So for this purpose, it's a lot less convenient to handle because you need an argon glove box, and very few people have those. So I'm going to put lithium in E tier. Now potassium is dangerous. Potassium forms peroxides that are shock sensitive. It also is way more explosive when it comes in contact with water, but it is a way better reducing agent than sodium. I have had reductions of very stubborn tetrathiacin bis disulfides with potassium, but you have to get the potassium to melt. And a potassium melt is a pretty scary thing to do. So good reducing agent, a little bit challenging to handle. I'm going to put it in C tier. Now, in addition to the borohydrides, there's some other special borohydrides that we haven't talked about yet. So one of those is sodium cyanoborohydride. Sodium cyanoborohydride is useful as a reagent for reductive amination. And so normally if you have sodium borohydride will reduce aldehydes and ketones, but sodium cyanoborohydride doesn't tend to do that in most cases because it's just kinetically slower as a reducing agent. However, if you have an imine or an iminium, especially if you have an iminium, the reductive aminations can happen a lot faster because those are decent electrophiles. So sodium cyanoborohydride is like a tamed version of sodium borohydride. Now, the one disadvantage is that it has cyanide in it, and if you ever work with it, you can instantly smell the cyanide, and it is sketchy. So I'm going to put sodium cyanoborohydride in C tier. Even though it's got better selectivity, it's just a little bit more toxic to work with. Now, sodium triacetoxyborohydride is really good. It's like a tamed version of sodium borohydride. It is less reactive towards water as well as like other H+ sources, while it maintains most of its nucleophilicity. So it'll have similar nucleophilicity to sodium borohydride. So because it's better, we'll put it in A tier. Plus there's acetates, that seems appropriate. Now, red phosphorus. If you're familiar with red phosphorus, even if you're not a chemist, you'll probably be familiar that people use red phosphorus in the synthesis of meth. The reason that red phosphorus is used is because when I2 is generated in the reduction of certain compounds, I2 can react with red phosphorus to convert into phosphorus triiodide. And under aqueous conditions, phosphorus triiodide is able to convert into hydrogen iodide and some sort of phosphoric acid derivative. It could be hypophosphorous acid, it just depends on the conditions, which is why there's the hazard of forming phosphine gas when you're doing any red phosphorus reduction. So I'm going to put red phosphorus in D tier because it is also used for making drugs. Although you could also use it for lighting matches, but that's not really, relevant in this case. So iron. Iron is a good reducing agent. You'll see it used in the reduction of nitroarenes. So it's one of the more common methods to use iron and HCl to reduce a nitro group. So iron's pretty decent. It's kind of everywhere, so it's pretty chill. I'm going to put iron in S tier. Now, diphenylsilane. So diphenylsilane is an SiH type compound. You occasionally see these in organic synthesis when no other reducing agent will work. It's a little bit inconvenient in terms of having a lot of extra mass in those phenyl groups, and I would still say that even in reactions that do work with diphenylsilane, they don't usually work that well. So best case scenario, this is going to probably be an E tier. Now, triethylsilane, on the other hand, is a better silane. And so you will see quite often in medicinal chemistry, in the synthesis of compounds that medicinal chemists do, the use of trifluoroacetic acid in conjunction with triethylsilane. And so this gives you an H+ and an H- that tolerate each other simultaneously. And so you can oftentimes do reductions with triethylsilane and TFA and DCM that won't work with reduction with other reducing conditions such as LAH, alane, etc. So if you're having a challenging time trying to do some sort of reduction, nothing's working, it might be worth giving triethylsilane, TFA, and DCM a shot. And if you're not sure what conditions to use, someone in the Discord would be happy to help you. So I personally think triethylsilane is like one of the reducing agents of the future, so I'm going to put it in S tier. If you disagree, you can comment down below. Sorry about that. We also have TCEP. So I, as an organic chemist, have never worked with TCEP, but I'm familiar that biologists use this for reducing disulfides, kind of similar to how they use mercaptoethanol. Now, the advantage here is that this is likely less volatile, but it is still a phosphine, so I don't know in terms of like most utility for chemistry how much you'd want to use something like this outside of specific bio applications. So I'm going to put it in F tier. If you think I'm being too harsh for TCEP, make sure you comment down below so that I can learn something. Now, in the oxidant tier list video, we talked about potassium ferricyanide, but today we are going to talk about ferrocyanide. And so this is essentially an iron 2+ source that can be converted to iron 3+ in the presence of certain oxidants. It's a chill compound to work with. It's a salt. As long as you don't put it under very acidic conditions, it won't make cyanide. Pretty easy to work with. However, I'm not familiar with too many applications in organic chemistry for this. So for that reason, I'm going to put it in E tier. Now, we still have some more here. So if you've ever done an iodination or a bromination reaction before, you'll be familiar that we have to do some sort of protocol to deal with any excess iodine or bromine that remains. And so usually what we do is we use sodium thiosulfate to quench that, especially the analytical chemists among us will be familiar with this. So sodium thiosulfate, nice, easy to deal with. The one disadvantage is it can be unstable under acidic conditions, and sometimes it can form elemental sulfur in workup. And so a good trick to get away from the elemental sulfur is to put in some sodium sulfite, which will react with sulfur and make thiosulfate. So if you ever get sulfur crashing out from a thiosulfate reduction, you can just put in some sodium sulfite and that'll clean up your workup. So sodium sulfate's pretty chill. I think we can put it in S tier because it protects us from dying from the halogen, so that's good. Now, elemental sulfur. Elemental sulfur can be a reductant in organic chemistry. However, it can do a lot of chemistry. Sulfur is very promiscuous. At different temperatures, it'll do a lot of different things. I personally don't think that there's too much clean reactions that can be done with sulfur in terms of it as a reductant. And so for that reason, I'm going to put it in F tier. I'm sorry, sulfur. Zinc. Zinc is another really good metal for doing reductions. You can react this with acyl or rather alkyl chlorides. So if you wanted to do some sort of addition like the Reformatsky reaction, you could do that with zinc chemistry. Zinc in general can be used as a reductant to turn over catalytic processes if you need to reduce a catalyst back to its reduced state. Zinc is also widely available, and for that reason I'm going to put it in S tier. Usually you need to activate zinc. Now magnesium is fairly similar, except you're forming Grignard reagents. Zinc and magnesium can also both be used as reducing agents to deprotect N-tosyl groups or N-sulfonyl groups, usually with sonication, not always though. And so magnesium's another really chill one, and for that reason I'm going to put it in S tier. So hypophosphorus acid. I have never worked with hypophosphorus acid, however I'm familiar that it can be used in clandestine chemistry as well, and since it's used in clandestine chemistry, we're going to put it right into D tier because it's used for making drugs. Sodium dithionite. This is a reagent that old school labs have, and usually it's stored in a flammable solid cabinet, but no one's really sure why. Now, this is a really potent reducing agent. You can see this is actually a 2-electron reduced form of sulfur dioxide. And so there's a paper that shows this can reduce ketones and aldehydes, but for the most part, it doesn't see too much use in organic chemistry. Now, because it's hazardous and it doesn't see much use, I'm going to put it in F tier. Dithioerythritol. This is another bio-based reductant, and what biologists typically do is they'll take disulfides and reduce them to thiols with dithioerythritol. Eventually the equilibrium will bring it to a point where this will form its own disulfide, and then that could just be removed in washes. So because it's a bio one, it's a little bit less interesting. However, it's not going to be anywhere near as volatile as mercaptoethanol. So I'm going to put dithioerythritol in E tier. TMSS. TMSS is tris-trimethylsilylsilane, and this is kind of like a reagent of the future to replace tributyl tin hydride. So if you ever need to reduce a carbon radical, you can reduce a carbon radical with TMSS. That'll just form a CH, and then you'll form a silyl radical that can go and do other chemistry. So TMSS, really good reducing agent. I'm going to put that in S tier. Tributyl tin hydride, as we were just talking about it, is kind of the same thing. You can quench a carbon radical with a hydride if you want to do that kind of reduction. Now, the disadvantage with tributyl tin hydride is that unfortunately it has tin in it, and tin compounds are very smelly and quite toxic. And so for that reason, I'm going to put tributyl tin hydride in B tier. Now, some other boron-based reductants include superhydride and selectride. So you can get a lot of different metal forms of selectride, such as K-selectride, and usually when you're using the selectrides, you just screen a bunch of them. Now, these can be better for diastereoselective reductions of certain ketones near stereocenters or aldehydes. And so you might want to use selectride if you're getting a low DR in some sort of reduction. So the one disadvantage for the organoborane hydrides is that they form boranes as byproducts, which are highly flammable and kind of a pain to deal with. So selectrides can go in C tier for that reason. Same with superhydride. These are very reactive, though. These can be more reactive than the borohydrides too, and they have better organic solubility. Now, borane is really toxic. It's a volatile form of borohydride. It usually exists as diborane on its own, but it's also available as a number of different complexes. You can do hydroboration reactions, which are really useful in organic chemistry. And because it starts with a B, we're going to put it in B tier. Now, we have a couple ones left, so we'll try and zip through some of the easy ones. Water is in soda, right into S tier. You might not think of water as a reducing agent, but plants convert water into O2. So water's got to be S tier. I wouldn't be breathing right now if it weren't for oxygen, so water's got to go in S tier. Now, if you wanted to use solvated electrons, you can do what's known as a birch reduction. And so you can take something like ammonia and condense it into its liquid form, anhydrous ammonia, and you can actually dissolve alkali metals such as sodium or lithium or potassium into the ammonia, and you get this beautiful blue or copper colored solution. It looks like copper metal, it just depends on the concentration. So solvated electrons can do what's known as a birch reduction. We typically try to avoid birch reductions because they can be fire hazards. I personally know someone who has had a number of fires as a consequence of their work doing birch chemistry, but that might have to do less with the birch chemistry and more with the chemist doing it. So really cool, but a little bit dangerous, especially with the liquid ammonia, because ammonia can be quite toxic to handle. But it's still pretty cool. I'm going to put solvated electrons in S tier just because they're so cool. They're one of the coolest things in organic chemistry. Carbon. So carbon is used to reduce metal oxides into their metal zero form. It's also used in several applications as a reducing agent, decolorizing charcoal, similar, whether or not this is a chemical reaction that's happening with the charcoal or there's just like the absorption of impurities can be debated. But I think regardless, we can at least put carbon in C tier. Okay, zinc borohydride. So zinc borohydride is something you might not be familiar with. It's a little bit like sodium borohydride, except occasionally you'll see it used in total synthesis. And so the advantage here is you can get better diastereoselectivity, relative selectivity, which you might not get as much with sodium borohydride. However, because it has less use, I think we better put it in E tier. Carbon monoxide is terrifying. Can be a really good reducing agent, but it's a little bit too scary for any of us to work with unless we absolutely have to. I would never go out of my way to work with carbon monoxide. However, I do think it has a lot of untapped potential in organic chemistry. We just kind of forget that carbon monoxide exists, and sometimes the inorganic chemists will look at this to do, for instance, hydroformylation reactions. So carbon monoxide is actually quite cool, but it's very, very dangerous. And so for that reason, I think we have to put carbon monoxide in F tier. Now, triphenylphosphine can be used as a reductant as well, because the phosphorus would like to be phosphorus 5. It's currently phosphorus 3. This can do several reactions in organic chemistry. And the only thing that everyone hates about triphenylphosphine, other than its massive weight, is that it has a really difficult time being removed. So if you form triphenylphosphine oxide, it's like really hard to remove as a byproduct. However, there was a recent paper using calcium bromide, which can actually apparently do an even better job than the previously reported zinc chloride method for precipitating out triphenylphosphine oxide. I can put a link to that here if you're interested. Now, triphenylphosphine, it's used in so many reactions in organic chemistry. However, it's also used as a nucleophile, not just as a reducing agent. So for that reason, I think we're going to need to penalize it somewhat because it isn't a very selective reducing agent because it's a very good nucleophile. And so I think we better put it in C tier. Now, hydrogen sulfide. I would never want to work with hydrogen sulfide as a reducing agent. I think there's just better reducing agents that you can use. Occasionally, you'll see nitro group reductions with hydrogen sulfide or sodium hydrosulfide or sodium sulfide, but the disadvantage of hydrogen sulfide is it's very deadly and it stinks. Hydrogen sulfide can go right to F tier. We also have sulfur dioxide, which is a little bit similar. So sulfur dioxide isn't used too much in organic chemistry as a reducing agent, but occasionally you'll see it reducing things like the halogens to sulfuryl halides. Because it's also really toxic and it smells terrible, we can put that in F tier as well. Now we've got a few left. So you got glucose, isopropanol, zinc amalgam, and triethyl phosphite. So a Hunch ester is this dihydropyridine, and you can see this really wants to be aromatic. So this is a little bit like NADH in biological systems. It can be a good hydride donor. And I think that the Hunch esters and related dihydropyridines just really have a lot of untapped potential in organic chemistry. Yes, they're getting explored, but I think that they should be used more and more because they're very easy to make. This is a really good reductant. It could be tuned. A lot of known enantioselective reductions have been demonstrated with Hunch esters. I think Hunch ester probably belongs in A tier. Let me know what you think down below. Isopropanol, you might not think of as a reductant, but there's a reduction called an MPV reduction, which is the opposite of an Oppenhauer oxidation, where in the presence of isopropanol and an aluminum isopropoxide catalyst, it's possible to reduce ketones and aldehydes to the corresponding alcohols, and then the conversion of isopropanol into acetone. So this can just be used as a solvent, and it's also a reductant for those transformations. Now, because of how convenient that is, I think isopropanol has to go in A tier. Now we got 3 left: glucose, triethyl phosphite, and zinc. Glucose is a reducing sugar. Biological systems are able to do reductions with it. You know, it's our source of energy that we are slowly oxidizing into CO2. And because glucose is in soda, we're going to put it right into S tier. Okay, so we got a zinc amalgam. Certain reductions can be done with zinc, but sometimes the reductions don't go that well. That could be because there's zinc oxide on the surface. It could just be because it's a solid and there's not that much surface area. And so one of the things that you can do if a certain reduction isn't working well with a metal, you can make an amalgam. And so the mercury just provides more surface area because mercury is a liquid. So zinc amalgams can be quite good for certain reductions. Now the disadvantage is there's mercury. And the attitude that most of us have is maybe let's move away from mercury whenever possible. So for that reason, I'm going to put the zinc amalgam in E tier. Now, last but not least, we have triethyl phosphite. Triethyl phosphite is like triphenylphosphine, but again, the disadvantage here is that it's got a lone pair. It's going to be doing nucleophilic chemistry as well. But that being said, triethyl phosphite can be a good reducing agent for certain applications. Nonetheless, I'm going to put it in E tier. So hopefully you've enjoyed my critique and tiering of the different reducing agents, aka antioxidants. If you like this video, it would really help out the channel if you could leave a like and subscribe, and I hope you have a great day.